So these drag races that you occasionally see in these arenas often seem to follow these rules. But this is all correlative. How do we actually test these hypotheses? You need a robot, right? This is where you kind of get into behavioral robotics. So we started to build this structure we call Flyatar. And the fly is just a little tiny fly-sized magnet that's controlled by a series of motors underneath a platform. So we can move the motor around and have it interact with a real fly. And we have a visual surround. This is all the work with Peter Polidoro. And Cisco is now part of the team. And I can talk about the details of some of the open source engine that we use to operate this whole thing. But let me just show you an operation. So basically, in order to do this in real time, you need to have very good real-time tracking of the fly, because you can't make gross errors in your estimate of its motion and position, or it'll kind of screw up the feedback loop. So here's just an indication that we can track this real fly with its orientation. And again, there's kind of math techniques of how we do this in a robust and integrative way. So in order to have these behavioral interactions, we need to drive the robot in the fly's frame of reference. And this is just sort of a little demonstration of that. So we're sort of giving commands to go to different positions in a polar coordinate system surrounding the real fly. So we're sort of driving the robot in the fly's frame of reference. Now the fly starts to move. And of course, the frame of reference moves with the fly, so the robot has to catch up. So these are sort of the primitives that we need to have these sort of social interactions. So then, like a very simple thing you can do is have like little chases. So you can program the robot to just follow the fly. Now we let the fly alone when it's near the barrier, but then the robot will sort of follow and chase the fly around the arena. So you can see much fun ensues. So I don't have much data left, but I can at least begin to show. To test this regressive motion hypothesis, obviously we have to do this very quantitative way. But here's some experiments where we sort of perform drag races with the fly, and we just sort of go around like making the fly stop, right? It looked like we ran over the fly. Anyway, you get the idea. Now to do this well, I mean, the thing is, if something's moving very fast, progressively, fly should pay attention to that too, because it probably means that if something's moving much faster than the sort of expectation of the world moving by you, you should pay attention to that. So this is sort of a formalization, if you will, of what I think the regressive motion sequence hypothesis would look like. If an animal's moving, then sort of a probability of stopping should increase with the angular velocity of this object. And that the threshold for that sort of stopping should be much higher for regressive motion than for progressive motion. And then again, very high velocities, it's all going to fall off because of sort of the limits of motion detection in insects. So that's it. I don't have any more data. This is the hypothesis that we're going to test, and we're sort of setting up experiments to do that. And I want to talk a little bit about future directions. I mean, once we can sort of get these sort of simple proof of concepts, there's lots of interesting things that we want to do. For example, it's not going to be hard at all to add odor to the robot. So you've heard a lot of stories in courtship of sort of the importance of olfactory information, either tactile olfactory information, volatile olfactory information. We can actually endow the robot. We can make it more visually realistic. We might even put little kind of hydrocarbon-coated legs. So we can begin to test some of the sort of hypotheses about how you get complicated behavioral sequences in courtship, for example, or regression, using such a robot. We've heard about social interactions. I think it's very interesting to sort of put a robot in with a bunch of flies, right, and then see how the behavior of one individual can modify the behavior of the group as a whole. So I'm basically done. I want to thank Peter Polidoro, who's the chief engineer, who designed the Flyatar, Pietro and Kristen and Alice, who are the collaborators on the C-Trax project. Andrew Strahl has done this wonderful technology development in the lab and good science. Mike Reiser and Jasper Simon. And let's see if I have, there's one more thing. Okay. So just to end on a positive note. So if you think this is sort of like, behavioral robotics is just a crazy thing, it's sort of an emerging field. And this is one of the sort of more interesting applications. So old people live longer if they have pets. This is true. But old people, after a certain time, can't take care of pets. So there's actually a funded project in Japan to build robots that interact with humans, that are like where the interaction is salient enough that the human would get the benefit of the interaction with the pet. But of course, you wouldn't have to feed the robot. I mean, you might have to change its batteries or something. But so this is Pero, this robotic baby seal that interacts with a human and evokes certain emotions. Oh yeah, and this is set up. Oh, actually, the feeding is done, so you have to give it a little pacifier. That's actually how it gets its energy. There's another one. So, okay, as silly as these things are, but I mean, it is interesting. I mean, the point of these robots are designed that their behavior modifies depending upon their interactions, with human. So the idea of giving Jane a robotic chimp, ultimately it's not as crazy, as initially sounds. And I think maybe, Drosophila is maybe a good starting point for, developing this